Hello everyone and welcome to this lecture. Today we are going to talk about a method to solve non-homogeneous second order differential equation, and this method is known as the variation of the parameters. So far we have seen second order differential equations with constant coefficients, and it's a bit hard when the coefficients are not constant, and we also saw some non-homogeneous equations, and we discussed a method called method of undetermined coefficient in the previous videos, but today we are going to look at something called a variation of parameters. And in this method we are going to see that we can symbolically solve whenever there is a non-homogeneous term is appearing on the right hand side of the differential equation. And to do that, what we are going to do is that first we will write our differential equation as, let's say, like this: y double prime of t. This t will be our independent variable, and then what we're going to do, we are going to, instead of taking the constant coefficients, now we're going to consider something, a function. So this p of t can be a number as well, and that will reduce down to the constant coefficient problem that we have dealt so far. And similarly we'll have a y prime over here, and finally we'll have some q of t, and there will be a y of t, and this will be equals to some f of t. So if you recall, this is our non-homogeneous term. This is the thing that is making this differential equation into a non-homogeneous differential equation. So let me just write that. Now if you consider the homogeneous equation, this means the function f of t will be just 0. So the equation will now reduce down to this. Note that I am not writing the t explicitly now, because it is well understood from this line that they are a function of t. So the homogeneous equation will look something like this. And the solution for this homogeneous equation over here, we are calling it the complementary solution, and it is denoted with yc with some constant over here. This is y1 and c2 y2. Note that this y's, y1 and y2, they will be time dependent, or so to say t dependent, while the c1 and c2s are determined by the initial or the boundary conditions. Now the question is, what happens when you have this non-homogeneous term over here? So if you recall that there should be a particular solution for the non-homogeneous term, so we write the non-homogeneous term will give us a particular solution, and we are calling that particular solution as yp. This is our particular solution, and the full solution to the differential equation will be yc plus yp. This is our full solution, and our main goal is to identify this yp with the method of variation of parameters. So let's try to now dive into the theory, and we'll see example in the next video. So our yp of t can be written as the following: u1 of t, y1 of t, u2t, y2t. Why it is like this? Because if you recall from solving the first order equations, we assumed that there should be a form of particular solution that will work, and this is that form. And here this y1 and y2 are coming from the complementary solution that is over here, and this u1 and u2 are the things that we need to find. So let me just write that down. We need to find u1t and u2t. And also note that the full solution that is over here, this satisfies the differential equation. And if you plug this into the differential equation over here, that is this guy, you will get a decoupled solution. The decoupled solution in terms of the complementary solution that is coming from this homogeneous part and the non-homogeneous part. So the non-homogeneous part, that is the yp, they will have a form like this. If you just plug it back and do some algebra, that is, you differentiate and you just decouple the terms. So the non-homogeneous part will be something like this. QYP is equals to F. And the homogeneous part will look something like this. So we are assuming we have already solved this part. This is an assumption. Now we want to solve this guy. And we want to find our u1 and u2. So let's get down to it. To find u1 and u2. So finding u1 and u2. So first what we're going to do, we are going to evaluate y prime of yp prime, that is the first derivative of yp. And if you recall that yp was written as u1 of t, y1 of t, u2 of t, y2 of t, like this. So now you want to have the first derivative over here. So this will be u1 prime, y1, u1, y1 prime, and then you will have u2 prime, y2, then u2, y2 prime. After that you want to evaluate the second derivative, right? And the second derivative will be u1 y1, and there will be a prime on both. Then you will have u1 double prime, that is from this part. You will have two parts over here, so you will have u1 double prime and y1 over here. Then you will have u1 prime, y1 prime, and then you have u1 y1 double prime. Similarly for u2, you will have, that is this term and this term, you will have u2 double prime y2 plus u2 prime y2 prime plus u2 prime y2 prime, then u2 y2 double prime. And now what we are going to do is that, let's call this equation 1, this is equation 2, and this is, let's see, equation 3. We are going to use 3 of these equations, and we are going to use this equation, let's say call it A. We are going to put this derivative, that is y double prime, y prime, and y over here, and then after doing some algebra we can find out some expressions. Hopefully we can find out some expressions that will help us to resolve what is u1 and u2. So let's try to do that. So let me write the whole thing again. This will be y double prime, this will be py prime, and this is qy. Obviously these are the particular solutions that we are looking for, and we'll have our f. Now if you write things down, and that is you write things down from equation 3, equation 2 and equation 1 and collect all the terms, you will have u1 y1 double prime py1 prime qy1, then you will have u2 y2 double prime plus p y2 prime plus q y2 plus p times u1 y1 prime u2 y2 prime plus y1 u1 double prime y2 u2 double prime plus 2 u1 y1 prime over both and u2 prime y2 prime, and this will be equals to our f, right? Obviously all of these are functions in T, and now you can see that since y1 and y2 both of them satisfy the homogeneous differential equation, this part will be 0 and this part will be 0. And now what you can write from these lines over here is that you can combine some of these terms, that is here you will have 2 times u1 y1 and 2 times u2 y2 prime, right? But what you can do, you can keep one of them outside this bracket and pull some of the terms on the inside, that is you have y1 u1 double prime and you have, so let me just write it down so that it's more clear to you. So you will have y1 u1 double prime, and here what I want to do right now is that I want to have u1 prime and y1 prime, and I want to mark this as something separate, and the reason will be evident very soon. Similarly u2 y2 double prime plus y2 prime u2 prime, then I'll have my u1 y1 prime and u2 prime y2 prime equals to f. Now what I can do is that I can write this term and this term as the following. Let's say ddt, and I will have my y1 u1 prime, this part, and this will be ddt of, that is coming from here, as y2 u2 prime, and again you will have your u1 prime y1 prime plus u2 prime y2 prime equals to f. Now derivative is a linear operator, so let's combine them. That is y1 u1 prime plus y2 u2 prime plus u1 prime y1 prime plus u2 prime y2 prime is equals to f. Now we have to impose some condition, and imposing y1 u1 prime plus y2 u2 prime equals to 0. This is the condition that we're imposing, and there is a reason for doing that, because we have two things to find out, that is u1 and u2, and we need at least 2 equations to do that, and this is a way to generate 2 equations out of this equation over here. And if you do that, that means if you take this part to be 0, that will mean, that is this part, if you are taking it to be 0, that will mean you will have y1 prime u1 prime plus y2 prime u2 prime is equals to f. Now we have 2 equations just by imposing this condition, right? And from here we can solve for, u1 and u2 primes, and after integrating we can get our u1 and u2. So let's do that. If you solve these equations over here, solving them, we will get u1 prime as minus y2 f divided by w, the Wronskian. And if you recall the Wronskian, okay, let me just be more explicit. The Wronskian of two functions is given by the following: y1 y2, y1 prime y2 prime. This is our Wronskian, and it will since it will not be 0, that will mean we will have two independent solutions, and u2 prime will be y1f divided by the Wronskian, that is coming from y1 and y2. So in principle we are done. So if you want to solve for u1 of t, again I'm mentioning the t explicitly here, and this is the derivative with respect to t. It's just the integral of minus y2 f by w, and u2 similarly an integral dt y1f divided by w. So this is the punchline. That is how you can get this u1 and u2 for the variation of the parameters. So this method is called the variation of parameter, and in general, whenever you have some function, you want to check whether there is a particular solution is attainable or not, and then you go on and use this method. So this will be the formula. Relevant formula for variation of parameters, and it will let us know whether we can have a particular solution. Because most often there will be some differential equations that even the homogeneous part is too difficult to solve by hand. These are notoriously difficult things whenever you have non-constant coefficients. Sometimes they can be very notorious to solve. So the least you can do is that check whether the function that is appearing on the right hand side of the equation presents us with a particular solution. So in the next video we are going to use these formulas over here, that is for u1 and u2, and we're going to see some examples using these formulas, that how we can attain a full solution or some partial solution. By partial solution I mean the particular solution for a differential equation of second order. So this will be it for today, and thank you.